All right. So our next speaker will be Ashvin Vishwanath from Harvard, talking about Moire magic near charge neutrality.
All right. So thanks. I actually missed a little bit of what Danny said, but hopefully you can all hear me now. And you can see my slides. Yeah.
Yes, looks good.
Yeah. Thanks, Danny. Yeah. So let me talk about something a little different from what I usually do in terms of theory for twisted bilayer graphene. So I'll be focusing on magic angle graphene, just like the first half of Pablo's talk, the bilayer, the twisted bilayer. But I'd like to tell you a little bit about our thoughts about the charge neutral point, which is particularly nice in terms of theory. And maybe it's not received as much attention because of a lot of the interesting phenomenology that has been seen so far in twisted bilayer graphene has been at other fillings. Okay, so I'll tell you about two projects. One is about a new kind of numerics that we've been able to do here for the first time, quantum Monte Carlo that lets you get to really large system sizes. I'll tell you some of the surprising results we have seen there, especially for the finite temperature physics. And then I'll tell you some general constraints from theory for superconductors that might emerge from the charge neutrality point. Okay. All right. So we had a nice introduction by Pablo, so I could skip a few of my slides. But I want to set a little bit of notation that you'll see going through this talk. So of course, we start with graphene. It's got two sublattices, A and B, and two valleys, K and K prime. And I'm going to denote those by tau for the valley and sigma for the sublattice. And when we have to refer to spin, we'll use S rather than sigma. So that's for a single sheet of graphene. And we know that all the excitement has been when you put two of these sheets together and twist them. And there were these theoretical studies that said, if you look at close to this magic angle of 1 degree, you get these extremely flat bands, and that's shown here on the left. So our interest, of course, will be when the chemical potential is inside these flat bands. There are two of them for the two valleys. You have the spin degree of freedom as well. And the interesting thing is there are a pair of bands that make contact over here that touch. So these are really the effective degrees of freedom, which we will be interested in. Okay, and that corresponds to the experimental figure on the right. And one thing I want to sort of make sure we all are on the same page is on the notation for the filling for this phase diagram. Okay, so on the x-axis, you have the density of electrons. 0 is the charge neutral point. And if you fill either in the plus or minus direction, add electrons or holes, and you have 4 electrons per Moire unit cell or 4 holes per Moire unit cell. Those correspond to completely filling or completely emptying these bands. Okay, so a total of 8 from the bottom to the top. And 8 comes from these 3 degrees of freedom, spin, valley, and the fact that you have 2 bands touching each other. Okay, so to remind you where the different phenomena are observed, so this is, let's say you begin at the bottom of this band, you have no electrons, and then you do electrostatic gating to get some electrons in. So your chemical potential floats up somewhere to the in the middle of this bottom band. That's where insulating-like behavior is often seen. That's called nu equal to -2. And a little bit below that in chemical potential is where most of the reports of superconductivity have appeared. That's shown in this nice review article that compiles many of these experiments. You see many of these superconducting domes on the left of this nu equal to -2 insulator. Okay, so a lot of people, including ourselves, we have focused quite a bit on this nu equal to -2 regime where, as Pablo mentioned, there are this cascade of transitions allows you to ignore some degrees of freedom. Okay, or at least that's the first approach. You can reduce the number of degrees of freedom in your problem. Okay, on the other hand, we also heard about, so this is the superconductor on the left. We also heard about the quantized anomalous Hall effect in the same notation. It's seen at equal to 3. That's this experiment over here by Andrea Young and following the experiment in Stanford. There's also a report by Dima F. in equal to 1, quantized anomalous Hall effect. Those occur at odd filling, so that odd integer is important over here. But what I'll be interested in is the charge neutrality point. I float my chemical potential up right in the middle of those bands, equal to 0. And we'd like to understand that point from the theory perspective, and also try to correlate it with some experiments that are out there. Okay, so so there is the first part. After I give you a bit of an introduction, the first set of results, if you like, will be on the numerical study of this charge neutrality point. So, and we'll also like to compare it to experiment. Many experiments are like the one shown over here on the left. They don't quite see an insulator at the charge neutrality point. They see something more consistent with the Dirac points, perhaps with some pneumatic kind of distortion. But in some experiments, like this one over here, an insulator is actually seen at charge neutrality. Okay, so there is some variation depending on maybe other parameters that we're not quite aware of, things like strain, for example, maybe at play over here. But anyway, both kinds of behavior have been observed. And then I'll also talk a little bit later at the end, if I have time, about theoretical considerations related to superconductivity if it appears near charge neutrality. Okay, so what does appear near charge neutrality mean? For example, there's this experiment from the same group. They see superconductivity, these small domes over here appear near the charge neutral point where an insulator is seen. And we'd like to understand what constraints are placed on such superconductors when there is no flavor polarization present. Okay, and that'll be the second part of the talk. Okay, but to set the stage, I'll have to review a little bit of background. So I've given this kind of background before. I'll go over it somewhat quickly, and we've condensed it into a pedagogical review that's on the archive where you can look for more details. Okay, so first, let me say a few words, a couple of slides about the single particle physics. Okay, and there's something special about the single particle physics of twisted bilayer graphene. Many ways to discuss it. You start with this continuum Hamiltonian of Bistritzer and McDonald. There are these Dirac Hamiltonians for each of the decoupled layers. I have this theta over 2 because these Dirac cones are rotated slightly with respect to one another. And then there's an interlayer hopping, T of R. T of R itself is a matrix, okay, because it depends on which sublattice you start from and hop to in the opposite layer. So there are two coupling constants over here, or hoppings, if you like, W0 and W1. And what was shown in earlier work is that there is lattice relaxation that reduces the W0, the hopping between regions like this, where the A and B sides are, where the A sides on the two layers are almost on top of each other, as compared to hopping in regions like this one, which look like Bernal stacked graphene. That's the coupling constant W1. Okay, there's some reduction. And what really exposes the physics of these flat bands, at least for theory, is to go all the way and suppress this hopping W0. Okay, and that's called the Carlo limit. That's sort of a fixed point, if you like, a theoretical fixed point, where it's easy to understand the physics, and we can expand around that fixed point. Okay, and to some extent, the question is twisted bilayer graphene really within the radius of convergence of their expansion, so that physics that is morally similar to this Carlo limit holds for the realistic system. Okay, so what is special about these flat bands? There's something about their quantum geometry that's rather special. So topological properties, but I feel this is maybe the best way, the quickest way to introduce this. So once you introduce this chiral model, it has a symmetry. There's a fixed matrix which anti-commutes with your single particle Hamiltonian. Okay, and that fixed matrix is actually just the sublattice matrix. So this gives you some special properties. One of them being that you can find a magic angle where the band is perfectly flat. It's not just very, very flat like you see over here, but mathematically flat. And you can determine that Angle, it's pretty close to what you expect for the magic angle. It's written in these units, this kind of dimensionless units. And in fact, you can get more precise. So there's some nice mathematics over here. So some of the mathematicians got interested, and they really cranked out exactly where this flattening happens. That's one aspect. The other aspect that's going to be equally important for us is what the wave functions look like in this limit. Okay, and it turns out in this limit there is it's really makes things a bit makes things transparent. You can go to the regular band basis for these flat bands. This is a pair of bands that are touching at some particular value k, and you can sort of shuffle these basis states around and go to a different basis where you get a pair of churn bands, okay, churn 1 and churn -1. Now, in itself, that may not be very surprising. You're just taking apart a band into opposite churn sectors. But what is important over here is that these churn sectors are actually sublattice polarized. Okay, so the churn 1 lives on one sublattice, the churn -1 on the opposite sublattice, and everything is reversed on in the opposite value. Okay, so because of this sublattice polarization, it'll turn out that interactions like this basis, okay, they can, by polarizing the electrons on different sublattices, they can lower the energy. So in the limit where the dispersion of the bands is not large, where you can take any linear combination you like, you end up preferring these when you have strong interactions. Okay, so that's sort of the quick motivation why we should change our point of view and go to this churn basis. Okay, so this churn basis turns out to be useful even away from the chiral limit, even when you start cranking up this parameter W0, cranking up the ratio away from 0. The sublattice polarization remains. It's not perfect, but it remains to a large extent. And a lot of this energetics goes through even away from the chiral limit. Okay, but that'll require a little bit of work and checking to see how far that holds. Okay, so to just give you a flavor of what the interaction problem looks like, so you have these density operators. You have density-density interactions with a screen Coulomb potential. The density is projected into the flat bands, and that's where the wave function of the flat bands appears, and they're hidden in this form factor, and that knows about the special properties of the flat band wave function. And because of the sublattice polarization, it's sort of like the density breaks up into a density operator for the plus and the minus churn bands. And that's perfect. This splitting is perfect in the chiral limit, and it's approximately true even away from it. Okay, so that really motivates this picture of the band structure. To the first approximation, we neglect the band dispersion, and you have this bunch of flat bands that are labeled by churn number, so churn 1 and churn -1. And in each sector, there is a fourfold degeneracy. Fourfold because you have 2 spin and 2 valleys. So there's a churn 1 sector with 4 bands, churn -1 sector with 4 bands. Okay, and the task now is to find states within this manifold that minimize the Coulomb interaction energy. And essentially what you get are generalized ferromagnets. Okay, it's not just spin anymore, it's a combination of spin and valley. Those you can realize in this, this picture makes it clear. That's really what you need to do. Okay, so depending on what filling you have, you've got to fill different numbers of these flat bands. For example, if you have charge neutrality, you're half filling. You have to fill 2 in each churn sector if you want a churn 0 state. If you're at equal to 2, then you have additional 2 bands that are filled. You have various combinations allowed depending on what combination of states you pick to fill, in this, what subset of these 4 you choose to fill. So that gives you a matrix that essentially captures the different kinds of ferromagnetic orders that you expect. You also notice that when you're at equal to 1, you're kind of forced into a situation where you have churn number. Okay, at least in the simple picture, the generalized flavor ferromagnets would end up having some non-trivial churn number. And this is broadly consistent with the kind of observations people have reported in small magnetic fields, weak magnetic fields. The kind of churn numbers you get are consistent with this sort of churn band picture, which gives us some faith that this is at least one of the preferred ways in which the system chooses to organize itself. Okay, so it turns out that in this picture, there's a large degeneracy. You can pick any state and of these 4 degenerate states, and you can make rotations between them. So there's a large symmetry, U4 times U4 symmetry in this ideal limit, where you have both in the chiral limit and in the absence of dispersion, absence of band dispersion. Okay, the realistic point is somewhere here. You have some band dispersion and you have some degree of non-chiral couplings, and you're trying to get there. And the way you do it is you start here. You have some sort of degenerate states, and you ask how these perturbations lift the degeneracy. Okay, so I won't go into the details, but there is sort of a hierarchy of energy scales that you can identify, and you can see how the symmetry is lowered from this large symmetry in the ideal limit down to the physical symmetry, which is simply spin rotations, and you can do the spin rotations independently in the 2 values. Okay, so the upshot of all of that analysis from this sort of strong coupling limit, if you like, with the perturbations, is that you identify a particular ground state, within this large manifold, which we call the KIVC, the Kramers intervalley coherent state. Here's a picture of this state. It breaks translation symmetry, not at the Moire scale, but actually at the graphene lattice scale. So it breaks. It's an intervalley coherent state. It makes a condensate, if you like, an excitonic condensate between the opposite valleys. The interesting thing is that the order parameter is actually in the form of a current. It's really the current loops that vary as within the carbon at the carbon lattice scale, and that variation is captured by this order parameter sigma y. This is off diagonal in the sublattice, tells you that these are currents that are flowing, and the tau x and tau y tells you this is a combination of the opposite values. So it's intervalley coherent, and we call it Kramers because of the way it transforms under time reversal. Okay, so in graphene, of course, you have the regular time reversal symmetry. You don't need to worry about spin orbit coupling. So the time reversal, if you like, squares to +1, just complex conjugation and switch the values. But the state over here breaks that time reversal. The currents reverse under time reversal, but there's a modified time reversal you can define, at least in the continuum problem, where you also rotate the value degree of freedom. Okay, and that modified time reversal squares to -1. It's kind of like Kramers time reversal. So this has this other time reversal present. That's why we call it Kramers intervalley coherent state. Okay, and it's also an example of a spontaneous topological instate. You start with bands that are partially filled. You get a gap. That's the gap that you see over here. This is the single particle dispersion. After the gap is opened, you fill all of these states below, and you have something that has a Z2 index with respect to this new time reversal, which is -1. Okay, so this is what is expected from the strong coupling analysis. It was verified in Hartree-Fock and other kinds of numerics. But there are some approximations involved over here, which is that we do have some dispersion of the bands, for example, and we'd like to know whether this rigorously holds for the realistic limit. Okay, do we really get this particular state? And also, how does it melt? As you heat it up, how does it melt? There were many questions we had that this particular analysis couldn't answer. Okay, I should also mention there was a very close competing state, which we called a pneumatic semimetal, which is you spontaneously break rotation symmetry, or if you have strain, the strain breaks it for you. Very tiny amounts of strain would, this state would win compared to the KIVC. And so this may be relevant to explaining some of the experiments. So there are these other competing states as well that I should mention over here. Okay, so this was the lightning review of the background. So now let me go to my results. Actually, maybe I should pause here very quickly for questions. Any questions so far?
Hey, Ashvin, this is Shankar. May I ask you a quick question?
Sure.
So wouldn't twist disorder play havoc with this, or is it an energetic question? Meaning that, that 2-axis diagram that you showed, where the realistic picture that is because of a little dispersion, the twist disorder is very relevant here, right?
Yeah, I mean, so this is, trying to keep as much of the realistic problem as possible without actually.
Oh, no. I love the theory. So I'm just asking you what's your opinion. I love the theory completely. I mean, you don't need to be apologetic at all. It's beautiful. But what do you think twist disorder would do is what I'm asking. What's your opinion?
I think one of the effects, one of the main effects will be that you get strain. So this the threefold rotation symmetry is, likely to be, broken to some extent. It's also seen in STM experiments where you can actually image the Moire lattice and you can see that it's not a perfect Moire lattice. There are other local probes that Pablo talked about.
Ashvin, you just muted yourself.
What happened to Ashvin?
Yeah. Can you hear me now?
You're unmuted.
Okay. You should go back to main talk. I get the point. So it can be actually systematically investigated if we have some idea about the symmetry of the strain. And usually there is some symmetry in the strain. That's what you're saying. Okay.
Yeah. So in fact, that was done in this paper by Parker et al. They showed that very tiny amounts of strain within DMRG, tiny amounts of strain, a few percent, the kind of strain you cannot rule out. And you see in some of the STM experiments, that kind of strain can switch you between the KIVC and the schematic semimetal.
Okay, thank you.
So this is nearby, and that maybe explains why some experiments see a gap and some don't. But yeah, these are things that I think it's important to realize in bilayer graphene, twisted bilayer graphene. People like to think of the angle as being the only control parameter. That's probably not true. Different experiments probably have other knobs that are slightly different that may be important.
Thank you. Yeah.
All right, so now let me tell you about these numerical calculations, quantum Monte Carlo calculations of twisted bilayer graphene at charge neutrality. So this was done in collaboration with Eresberg's group, and the heavy lifting was done by these two young people, Jonghyun Lee, who's a postdoc at KITP, and Johannes Hoffman, who's a postdoc at the Weizmann. So this was probably one of the most complicated numerical projects I've ever been involved in. But let me tell you the basic idea, just the overall, the approach. So what are we trying to do over here? I described an analytic approach to twisted bilayer graphene, but there are approximations there, and we'd like to, of course, verify these things in numerics. And what would we like to do? So we'd like to be as realistic as possible to try to model the actual system. Now, typically, as in the cuprates, people try to look at the Hubbard model. So here there is an obstruction to defining a Vanier description that is also fully symmetric, if you want to just include the flat band subspace. So there's a motivation there to work directly in momentum space. I think we'll hear from Oscar later about the progress in the, using the lattice description as well. But at least over here, we started from the start. We wanted to do a K-space approach. There are many degrees of freedom. Even at every K point, you have these 8 degrees of freedom we mentioned. This is a problem for many other numerical approaches. For example, exact diagonalization. This is just getting out of hand. So typically, you have to throw away some of these degrees of freedom. We'd like to keep them all. Also, we'd like to look at finite temperature effects. So a lot of very interesting effects people see at finite temperature in experiment. This Pomeranchuk effect, strange metal kind of behavior. We'd like to eventually access that kind of physics. Of course, there are many numerical approaches already out there, but we felt it would be very nice if we could do determinantal quantum Monte Carlo. So this is an approach where you can simulate hundreds of electrons if you like, but there's one big caveat. You need to make sure the system does not have the fermion sign problem. And if you can ensure that, you can do all of these things that I mentioned over here within this particular approach. Okay, and so what we managed to show is that indeed, with some small approximation, the simulation of twisted bilayer graphene and the magic angle can be done in a sign problem-free way, as long as you stick to the charge neutral point. Okay, and then you can get all of these things. You can do something that's realistic. You can keep all the degrees of freedom. You can do finite temperature, and you can do it directly in K-space. Okay, so there's some technical advance over here to be able to do all this. Okay, so let me just give you a couple of slides why this thing has no fermion sign problem, and that's actually related to particle hole symmetry. So I already talked about the chiral symmetry. In fact, if you have chiral symmetry, you can show the system has no sign problem at charge neutrality. But it turns out even without chiral symmetry, so chiral symmetry, of course, is strongly broken in the realistic system. Even without chiral symmetry, there's a different particle hole symmetry, which ensures absence of a sign problem. Okay? And the only approximation you need to do to get that symmetry, at least within our formulation, is you have to neglect these rotations of the Pauli matrix. Okay, two layers are rotated respect one another. Rotation angle is very small. In radians, it's 0.02. You're making an error of that, at most of that size. When you do that, when you neglect those rotations, you can show that there's an anti-unitary operator C, which changes the creation to annihilation operator. So it's a particle hole symmetry. It has certain matrices in front of the valley spin and valley sublattice and the layer. When you do this transformation, you can show that the Hamiltonian of the system, including interactions, is invariant. Okay, and it'll turn out that that is sufficient for us to show that there is no sign problem in the quantum Monte Carlo simulation. Okay, so one very important thing is that this particle hole symmetry requires you, what it actually does is that if you're at a filling nu, it relates the physics to the filling of minus nu. Okay, so in general, it's not a symmetry, it gives you a relation between two systems. But when you're exactly at charge neutrality, you get mapped back to yourself. And that's when it becomes a symmetry, and you can actually use it to make predictions and in our particular case, to actually show the absence of a sign problem. So what we could show is that even the full interacting problem with the density-density interactions, if you set up the zero chemical potential at charge neutrality, it has no fermion sign problem. So then you can go and simulate it. Of course, the simulation is not trivial, but there's no in principle problem with simulating hundreds of electrons. Okay, so very briefly, the way in which you do this simulation is that you have an interaction V. You want to find the basic object is this the partition function at finite temperature. You have this you have a trace over the e to the minus beta h. You do a Trotter decomposition into the single particle and interaction parts, and then you Hubbard-Sutanovich decouple these interactions. You write it like this. Where there's an integral over the Hubbard-Sutanovich field, which ends up giving you, just a rewrite of this problem. Okay, but there are these weights that come along with the Hubbard-Sutanovich field, W plus and W minus. These you get by integrating out the fermions. Okay, and what is completely essential for you to evaluate this partition function or evaluate, do Monte Carlo on this problem is that these weights are all positive. So, at the end of the day, the weight for a particular Hubbard-Sutanovich field is a non-negative number. It looks like static problem, not like a quantum problem. Okay, and what you can do is you can use the anti-unitary particle hole that I talked about to show that the weights from the opposite values are actually complex conjugates of one another. Okay, and when you can show that, essentially it shows that there is no sign problem in this for this case. Actually, even without spin, you don't have a sign problem. As long as you have these two values that are related in this particular fashion, and you can go ahead and do the simulation. Okay, we do the simulation with spin, but there are various extensions you can do where you can, which we talk about in our paper, where you can, go beyond this simple case. Okay, so so this is roughly how the simulation proceeds. You have these time slices in imaginary time, Hubbard-Sutanovich field defined for each time slice and for each momentum Q. Okay, and we can do grids, momentum grids up to 6 by 6. We can actually go to bigger sizes as well, but I'll show you up to 6 by 6. We have all like 8 electron flavors, and we go down to temperatures of about 2 Kelvin. Okay, and you can of course go to very high temperatures. That's not a problem. There's one technical aside, which is what is the single particle Hamiltonian that we include. So it turns out it's this the BM Hamiltonian, Bestreisser-McDonald Hamiltonian, but that is corrected by this Hartley-Fock decoupled interaction with the state that corresponds to the decoupled graphene sheets. Okay, so this is just something you have to do to avoid double counting. It's the simplest thing that you could do. So you go from a small bandwidth for the BM model to a larger one, effectively larger one. That's the bare Hamiltonian that you put in, the kinetic energy Hamiltonian that you put in. And of course, we can implement other schemes. We can test different schemes by including remote bands and so on, but I'll show you what happens here. Okay, so that is the setup. We have some kinetic energy term, which is somewhat larger than you might guess from just the single particle band structure. And we have an interaction term, and we'd like to know, for example, what is the ground state of the system? That's the first question. So let me show you some of the results. So we did a couple of cases over here with different bandwidths. So that's the x-axis. So this is our estimate of what the realistic model is at. This bandwidth over here, we also did another case with a somewhat larger bandwidth. What we found is that indeed, for this particular smaller bandwidth, we find that the ground state is ordered. As you go down in temperature, you see an order developing. This is the correlation length that diverges as you lower the temperature. Okay, so this is a log scale. This is 100 Kelvin, 10 Kelvin. And once you drop below 10 Kelvin, there's a divergence of the correlation length. Of course, the correlation length is bounded by the system size. So when you have a system size of 6, it climbs up to somewhere above 5. Okay, so this is a sign. The size dependence is a sign that in the thermodynamic limit at 0 temperature, you'll establish long-range order. The particular order that we found is the preferred one, is exactly the one that's identified in the strong coupling and Hartley-Fock theory. It's the KIVC order. Okay, so in this limit, somewhat small bandwidth, you actually recover, at least at 0 temperature, you recover what you expect. The interesting thing will come when we heat up this system and see how things change as a function of temperature. Okay, another thing I should mention, another bit of a surprise for us was when you go to the slightly higher bandwidth, we took a smaller value of kappa. Kappa is the ratio of this W0 over W1. Somehow in this regime, that ended up giving us a bigger bandwidth. Now it turns out the bare bandwidth is too much for the interactions, and you don't get an insulating state. Okay, so it's really a balance over here, which one is actually preferred. Hartley-Fock, of course, overestimates the order phase. Okay, so even with these parameters, it will predict an insulator with this KIVC order, but in this fully quantum calculation, it melts and you get actually a semi-metal. The correlation length is now finite, you can see, regardless of the system size, it doesn't scale with system size. Okay, so that was one surprise. So then the other thing we did was to look at the insulator, but on raising the temperature. Okay, so what happens there? Okay, so one quick thing I will show over here is that this strong coupling, at least in this regime, somewhat smaller bandwidth regime, is in very good agreement with what we expect from the strong coupling limit, at least at low temperatures. Okay, so if you were to go to this model with the enhanced symmetry, you switch off the dispersion and go to the Carlo limit, you find that many different orders are identical in terms of how they track each other as you lower temperature. Okay, this is a KIVC, this is our favorite order, but there are others like Valley polarized and Valley Hall that are degenerate according to this theory. They're all related by these U4 rotations. And that's exactly what we see in terms of, this is the order parameter magnitude that rises as you go to lower temperatures. And it rises in a way that's proportional to the system size, the area of the system. Okay, but when you go to the realistic point, you break down this large symmetry, and the only one that's picked out is the KIVC order. Okay, the other orders, for example, Valley polarized start rising, but then they realize that there's some anisotropy, they're not favored, and they drop in magnitude, and this is the ground state. Okay, so this ordering, if you were to pick a temperature where there is substantial short range order, that seems to be of order 10 Kelvin. Okay, that's when this correlation length increases beyond 1 Moire lattice spacing when you drop below around 10 Kelvin. So you can also extract the stiffness for these fluctuations. Okay, so now you can ask, what is the gap? What does the gap look like? So, naively, one would think that if you're below about 10 Kelvin, where the order is established, it would look gapped. It would look like the zero temperature ground state. If you're above that temperature, it should revert to the semi-metal, and you should have just thermal broadening of that semi-metal, but that's not what you see. So you can extract the single particle spectral function. This is A of K and omega, the fermion spectral function. At low temperature, indeed, it looks exactly like what you would expect. It's gapped. So this looks like the dispersion I showed you for the KIVC. There is some dip at the gamma point. In fact, these causes are for an interaction-only model, which you can solve, and it aligns quite well. And you see this dispersion where you get the maximum intensity, this dark blue, is rather different from the single particle dispersion. This red is the single particle dispersion. It should be gapless at the K point, but in this ground state, you find that it's actually gapped, and fairly large gap of around 40 millielectron volts at the K point. It's about half that value, or less than half that value at the gamma point. So this is what you'd expect, the gapped ground state. But now you heat it up well above the temperature where the correlation length is getting large. You go to 30 Kelvin, and it's not substantially changed. The single particle, you look at the gap at the K point, it still is fairly large, reminiscent of what happens at low temperatures. There's some filling in over here at the gamma point, this certainly sees the effect of these fluctuations, although their correlation length is rather small. So if you like, it's some kind of pseudo gap. There's no sign of order. It's fluctuating, but in the single particle spectral function, you see a stamp of this kind of order. Okay, and we see signs up to 100 Kelvin, so an order of magnitude larger than the scale where the short range order is set. Okay, you can also look at the correlated semi-metal. That was also somewhat interesting. So even at low temperatures, that state is very different from a slated terminant. Okay, so it's really a correlated state. To the first approximation, if you look at the C of K and omega, you see this dispersion over here. This is a free particle dispersion, and you get significant spectral weight, at those same points. Okay, and it kind of tracks that. But there is some spectral weight out here, which corresponds to the interacting model. Okay, so although it's predominantly looks like a semi-metal, gapless, etc., it seems to know about this gap that would have developed if it had become ordered. Okay, that's something we don't quite have a theory for. It's kind of reminiscent of these Hubbard bands, if you like, although there's no local picture, there's no local orbital kind of picture for this. Okay, so it would be very interesting to look at the transition. How do you go from this correlated semi-metal? When you reduce the bandwidth, how do you transition into the insulator? Okay, there's a standard theory for that transition. It's like a Gros-Neveu criticality, where you have a mass gap that opens at this K point. Okay, but at least from these two, from this particular spectrum, that's not what seems to be happening. It's not like this is losing spectral weight and you're getting some kind of a small gap that then increases. It seems to be there's already spectral weight transfer to begin with. So maybe there's a different way in which this transition is accomplished. Maybe it's first order. We don't quite know. That's one of the things for future work. Okay, it's also interesting to think about, maybe this could be measured, right? This is A of K and omega, what you measure in ARPES. Can someone try to do ARPES on these, on twisted bilayer graphene and, look at it in the same fine detail that people looked at other materials, like cuprates, for example. So it sounds a bit crazy at this point, but there's already some ARPES, nano ARPES on twisted bilayer graphene. Doesn't quite have the resolution for us to compare, of course. This is also at the bigger angle, but I think there is hope on the horizon for experiments like this to directly measure these kind of quantities. Okay, so let me conclude for this part. So what I talked about was the sign problem-free numerics for twisted bilayer graphene. The one restriction was that we stay at charge neutrality. I talked about these competing ground states, the insulator, the KIVC insulator versus semi-metal. In the future, we'd like to think more about these finite temperature effects. We talked about the pseudo gap already, but can we see signs of this Pomerancho type of instability that, in terms of the entropy, the linear T resistivity, and so on. And of course, things like the effect of strain, the quantum phase transition. Also, maybe we could try to look for skyrmions, in this in the system if those are low energy excitations. Okay, and of course, eventually, I'd like to compare to experiments. So let me just attempt a comparison with the STM experiments. So we didn't quite model this because there are strain and so on and so forth, and we calculated a slightly different quantity. So, but we can try to compare. This green curve over here is the charge neutral point within STM. So they are measuring density of states at some location in the Moire unit cell. And you see that they have these two peaks, right? That's reminiscent of a gap, and it has an energy of around plus or minus 20 milli-electron volts. So we can try to overlay that with our, integrate the spectral function over all momenta, get some rho of omega, and try to compare. So this is a different temperature. Just look at the most peaky one, that's the lowest temperature data. It does a fairly good job of reproducing this experiment. Okay, so of course, take it with a grain of salt because not all the parameters are the same, but there's a peak height is roughly similar, and there's a low density of states in between. But anyway, there is opportunity here to look at how the temperature evolution tracks these numerics if we can do finite temperature STM as well. Okay, so that was the conclusion for part one. Any questions on this part? Actually, Danny, let me check with you. How much time do I have left?
You have about 17 minutes left.
Okay, good.
So Ashwin, this is Jay.
Yeah, hi, Jay.
Hi. So valley polarized state is probably not one of the favorite phrases, but based on your sign problem, would there be an issue for this approach to see a valley polarized state?
No, there's no issue.
Imbalance? I see. So the fact that you needed the design problem relied on sort of this complex conjugation between values that's not an issue. I guess maybe if you wanted to calculate a correlation or something, a correlator of that in the partition function, it sounds like that could be a problem, no?
Yeah, that's a good question. So okay, so the sign problem thing that I talked about was for the generic case when I have no chiral symmetry and I have no and I have dispersion. So the valley polarized state is something that you would expect as a ground state if you had no dispersion, and you move away from this chiral limit. In that case, there are other transformations you can make. You don't necessarily have to do the one I talked about. You can make other transformations which eliminate the sign problem for the valley polarized state. So you see over here, the valley polarized is not picked out in the realistic case.
Yeah,
it is picked out in this larger symmetry case, and there, it's maybe related to that.
I see. Okay, yeah, interesting. Thanks.
Yeah, we have more discussion about this in our paper about different cases and where the sign problem is present, or when you can eliminate it with other transformations. Yeah, I didn't have the reference somewhere here. Yeah, there's also another paper by Zian Mong's group that also has some discussion maybe related to your question.
I see. Excellent. Thank you. Yeah.
Any other question? No? All right, so let me proceed to the last part, which is thinking about this question of what happens when you have superconductivity in a flavor unpolarized setting. So this is a work with Islam Khalaf and Patrick Ledwith, and it's on the archive. It's focused on twisted bilayer graphene, but I think some of these arguments are more general. We talked about 3 different outcomes that can occur when you have superconductivity in the absence, when you have this larger degrees of freedom. Okay, so it's most relevant for TBG if you're near charge brutality before the flavor polarizations set. Okay, so so just to remind you, I think Pablo mentioned this in his talk. There is this nice set of papers on the flavor cascade, where as you go away from charge neutrality, you start flavor unpolarized, let's say, and as you increase nu, you end up filling up one flavor. It could be spin, it could be valley, it could be spin valley lot. It's not very important exactly what that sequence is. You go into a flavor polarized state. And most of the experiments where superconductivity is seen after this flavor polarization occurs. Okay, so for example, you're at nu equal to 2. You say that, let's say the two spins are completely full. One of the two values of a particular spin are completely full. So you're left with essentially spin-less electrons. They're all spin polarized, if you like. And they have two values, and you're thinking about pairing in that setting. Okay, so in a way, that's taking us back to our familiar example of pairing between opposite spins, where value is playing the role of spin and there's no additional degree of freedom. Okay, but there are a few cases like this one over here, where there is superconductivity that appears near charge neutrality. And if you look at, for example, the Hall effect is the sensitive way of telling whether there is flavor polarization or not. It turns out there is flavor polarization, but it occurs in a regime that is beyond these superconducting domes. Okay, so the simplest interpretation is that these superconductors, you're getting pairing between electrons before the symmetry between the different flavors is removed. Okay, so can we say anything about that case? Can we, put some constraints? And that's essentially what we did in this paper. We said that if you have this flavor symmetry preserved, you have one of three options. You can either get something known as non-unitary pairing. So non-unitary pairing essentially is, an example is when you have pairing between the same spin. Okay, so you get different gaps for different spin components. The size of the gap is different. That's essentially what happens, if you like, in the flavor polarized states. You forget about one spin and you only have pairing between, let's say, spin up. But it could happen even in the symmetric case. It's usually not preferred because you don't get that much condensation energy. Okay, it's just something to keep in mind. The other two options are you get a charge to the superconductor, but because of the enlarged symmetry, having these many flavors, the order parameter is non-trivial. It transforms under these other degrees of freedom. And one consequence of that is that you can make fractional vortices. Okay, so instead of having the fundamental vortex HC over 2E, you could make a vortex which is HC over 4E. Usually that would be a problem because the superconducting condensate changes sign. Take a Cooper pair around and change sign. But you can tie that in with a change of the other degrees of freedom. And together they can end up giving you single valued phase for the Cooper pair. Okay, it's something very familiar from helium-3. But this is something that we would expect in this situation if you have a charge 2e superconductor. Of course, another way to get around this is to have a charge 4e superconductor that evades, you can make a fully symmetric condensate, but again, that would give you a fractional vortex because it's a larger charge condensate. Okay, so the way this proof works is, let me just sketch it over here. You can rotate these, you have a pairing matrix, you can rotate these electrons by whatever symmetry you have. It's simplest to think of a U4 symmetry, although actually U4 is broken ultimately. But just for the argument, let me say that there's a U4 symmetry, which, for example, you would get in the chiral limit. Okay, and it's very easy to see a Cooper pair will always transform non-trivially under SU4. You have two fermions that transform under SU4. You put them together, you cannot get a singlet. You have to get something that transforms either under the 6 or the 10 dimensional representation of SU4. It essentially tells you that the charge 2e condensate always breaks the SU4 symmetry. And then the superconducting manifold, the pairing manifold you get is non-trivial. And it's easy to see it admits fractional vortices. Okay, of course, you could make a charge 4 superconductor that's a singlet for electrons transform under the fundamental of SU4 can be in a singlet of SU4. So in this particular case, you don't break any symmetries. Okay, so these arguments are very easy to make for the case of SU4 symmetry. That's not what we have. The symmetry that we have is actually SU2 spin rotation. And if you ignore Hund's coupling between the two valleys, so if you say there's independent spin rotation in the two valleys, you can extend it to SU2 times SU2. Okay, and it turns out these conclusions are unchanged when you have the symmetry, when you have this independent spin rotation symmetry, which is very close to what is physically present. Okay, now if you add some Hund's coupling, it could give you a splitting of the, for example, the SU4 times SU4. If you have a Cooper pair where the electrons live in opposite valleys, you can show that the singlet and triplet are degenerate. Okay, and that's a consequence of this SU2 times SU2 being essentially SO4. So the order parameter there transforms as a vector of SO4, 4 components, 3 are triplet, 1 is singlet. Okay, now depending on what the coupling, the way in which this SU2 times SU2 is broken by these very weak Hund's couplings, you could either get a triplet or a singlet. Okay, so at the lowest energies, you could get something that is a singlet and doesn't break any symmetries. But then these fractional vortices would be, they would be excited states, but with very low energies, depending on how, depending on the strength of this Hund's coupling. Okay, so those kind of fine arguments are made in the paper, but at the maybe the simple statement to take away is that whenever you have this flavor symmetry, you have this enlarged symmetry coming from valley degree of freedom. You should be aware that these are very likely options, at least from the symmetry point of view. Okay, so we'd of course like to see this within a microscopic theory. For example, could you get a charge 4 superconductor naturally in the setting? Could you get charge 2 that breaks these other symmetries? Of course, to get charge 4 superconductivity, you need a strong coupling theory. You don't get that in a weak coupling theory. So we talk a little bit in that same paper about a skyrmion mechanism for charge 4 superconductors. So again, this is sort of the ground state manifold that we talked about. You fill 2 bands of churn 1 and 2 bands of churn -1. So the order parameter, if you like, is essentially this matrix. Sorry, this typo is 0 here. Diagonal matrix, you empty 2 bands and you fill 2 bands. And you can make any U4 rotation of that. That's the U over here. Okay, except that certain rotations do nothing to this matrix. This is an identity matrix over here. So the manifold of ordered states over here is U4 quotient with U2 times U2. Okay, so it's just a more complicated version of a point on a sphere. And just like the point on the sphere, which has skyrmions, this manifold also has skyrmions. Okay, and you can show that there are both charge 2 and charge 4 skyrmions, which are equally comparative, at least in the simple version of this theory. Okay, so you can come up with a microscopic route to thinking about this charge 4 kind of condensates, which may be present, potentially present in these systems near charge neutrality. Okay, so the main point I want to make over here is that it's important to distinguish 2 cases when you have orbital degrees of freedom, superconductors with and without flavor order. Okay, and when you do not have flavor order, interesting things can happen, and in some sense they must. When you have weak spin orbit coupling. And experimental consequences, obviously, we would like to make sure that the Fraunhofer periodicity people see for these superconductors are what you'd expect from the usual case, the charge 2e case. That's something that one would like to check. And also fractional vortices, maybe if there's scanning probes that can look for fractional vortices, these are a good place to look, I would say. Okay, so let me conclude with, already mentioned a few of the collaborators in the specific projects. These are others that we have worked with over the past few years on twisted barrier graphene and related topics. Okay, let me stop over here.
Great, thank you, Ashvin, for an excellent talk. Let's open up the floor to questions now. Are there any further questions at this point? All right. Well, since we had some questions during the talk, why don't we thank Ashvin again, and now we can take just a couple of seconds to move on to the next speaker. Thank you.
Right, thank you.
All right.